Okay, so today we will begin chapter 2, resistive circuit analysis. The first, I think the first few topics are still based on the material that you have already covered in your prereq classes, which is resistors in series, resistors in parallel, and then series parallel analysis technique. But I will go over those in class anyway. Okay, so let's go over to the class notebook. Okay, resistive circuit analysis. So first we'll look at resistors in series, then resistors in parallel. Okay. So the first thing is, how do we determine when two components are connected in series? Anyone? Add it up, yes. But identifying two components connected in series, we first look at the node. Node is, of course, an electrical junction where two or more components are connected together. But for two components to be in series, there cannot be more than two connections at a single node. Okay. So again, an electrical node cannot have more than two connections. So for two components to be in series, they have to be connected at a single node, and that node cannot have more than two connections. If there are more than two connections, then they are no longer in series. Okay, that's the first identifying mark. So if we look at this connection right here, it's a connection between R1 and R2 and R2 and R3. You have three resistors. The connection between R1 and R2 is a series connection because you only have two connections at that node. Only R1 and R2 is connected at that node. Let me label these nodes. Let's call this A, B, C, and D. So between A and C, if I was to measure the resistance, RAC, I can state that R1 and R2 are in series. And to add resistors in series, it's simply the sum of the two resistors in series, R1 plus R2. Same thing for RBD is R2 plus R3. Right? Familiar? Right? Okay. And then of course RAD, which encompasses R1, R2, and R3 together, but as long as they are all in series, we can still add them together. R1, R2, and R3. For series connections, you can have infinite number of connections. Or infinite elements connected in series, as long as that rule is still maintained. And between the outer two terminals, we can say they are still in series. Now, many books would take the notation of RT or R total. Sometimes in these slides, you would see R total. More often than not, you would see a notation called REQ. REQ simply stands for the total equivalent resistance as measured between any two terminals. So in this case, if you try to measure, Req between these terminals, the total equivalent resistance as measured between those terminals, I would note it as Req. Req is simply R1 plus R2 plus R3. Right? Current in a series circuit always remains the same. When it say always remains the same, it doesn't mean that the value wouldn't change if the values of the resistance would change. When we say the current is the same, it refers to the current for all components in that series connection. Okay. The total current in a series connection is a result of all of the components working together. It's the combined effect. It's a cumulative effect of all the resistors or all the capacitors or all the inductors in that series connection. But logically thinking, does I have any pathway to go except through R1, R2, and R3? So that current has to be the same. But it is a result of the cumulative effect of all three of them working together. If you take out one of the resistors in a series connection, the current value will change, but that value will be the same for all components in that series. Make sense? Okay. Speaking of remaining the same, if we go to a parallel connection, voltage remains the same. So here we can write current remains the same. And for a parallel connection, I can write voltage remains the same. And when I use the word remains, it doesn't mean that if the value of the resistors or the number of resistors changes, then the value will also change. The combined effect of R1, R2, and R3 connected in parallel gives me a resulting voltage, and that voltage is the same for all three resistances. If I add more resistors in this parallel connection, or if I take some out, then my voltage will change, but it'll still be the same for all elements in that parallel connection. So how to identify parallel connections? Well, I like to say that any two terminal elements to be in parallel, they have to be holding hands. The only elements that we see in this class is resistors, capacitors, and inductors. They're all two terminal elements. Okay. One terminal, two terminals. And so if each one of those terminals is connected respectively to the other component, then they are said to be in parallel. Or I would say both terminals of components have to be connected together. Must be connected together. Okay, must be connected together. And in this case, again, we measure the total equivalent resistance Req between those outer terminals. In this case, it doesn't matter. It's parallel, right? So if it's parallel, it's the same connection. How many nodes did we count here? Actually, two, right? Node is where two or more components come together. So we say B and C. And then the outer two terminals are the terminals of measurement A and D. If you measure the resistance between different nodes, then your resistance will change. But in a parallel connection, how many nodes do we have? Just two. It's parallel. It doesn't matter if you have 100 components connected in parallel. If they are in parallel, they must be connected by their respective two nodes. And so parallel connection will only have two nodes. You can have 1,000,000 resistors connected in parallel, it's still only two nodes. That's it. So it doesn't matter where you measure the resistance. Electrically speaking, it's the exact same node. You can measure it. You could measure it across R1, or you could measure it across R2 or R3. It doesn't really matter. Okay, important concept to keep in mind. Does that make sense? Right? So our EQ in this case is, well, as it is given here, it is the reciprocal of the sum of the reciprocals of the resistors in the circuit. You can have infinite number of connections in parallel, infinite number of components in parallel. It's still the same parallel connection. Okay. If you have two resistors in parallel, shortcut is REQ is the product of the two divided by the sum of the two. 1 over R1 plus 1 over R2 would give you R1 plus R2 divided by R1 times R2. You take the reciprocal. The resulting equation is the product of the two resistors divided by the sum of the two. This only works if you have two resistors in parallel. Also, another tip, if you have n number of resistors in parallel, if you have n number of resistors in parallel, all with the same value, REQ is simply R divided by N. Okay, you can easily do it with like two resistors, 10 ohms and 10 ohms in parallel. It's 1 over 10 plus 1 over 10, 0.1 plus 0.1, 0.2. Reciprocal of 0.2 is 5. 10 divided by N, in this case, N is just 2, gives you 5 ohms. 100 resistors, all connected in parallel with the exact same value. Let's say 1,000 ohm, 1 kilo ohm resistor. 100 of them connected in parallel would simply be 1,000 divided by 100. You can calculate. But that's another tip. If you have n number of resistors all connected in parallel with the same value, it's R divided by N. Two other things related. If you have R1, R2, and R3, 10 plus 10 plus 10, resulting value is 30 ohms. 30 is larger than 10. Our brains do not have to think about that. We never question it. Always larger value. We would never expect a smaller value because you're adding, you're summing up. In a parallel connection, when you add up resistances, the resulting REQ will always be smaller than the smallest resistor in that parallel connection. This is something you need to train your brains to look out for. These concepts will hold you in good stead. Okay, so when you're solving problems, these concepts will be a quick verification on whether your answer is correct or not. If you add up three resistors, well, two or more resistors in parallel, the resulting REQ will always be smaller than the smallest resistor in that parallel network. If you get something equal to or larger, then you know you You should immediately train your brain to think that my answer is incorrect. And we'll look at a few examples. So take out your calculators. If you don't have a calculator, take out your smartphone with the calculator app, and you're going to solve this, and you let me know what the answer is. So for A, we want to find the total equivalent resistance as seen from a pair of terminals. So in each of the circuits, in A, the terminals are on the far left. The terminals could be anywhere, okay? If you change the measurement terminals, your REQ will change. Again, another important concept to keep in mind. So depending on where you measure the terminals, measuring, when I say measuring or calculating, if you imagine if this was a real life circuit in a lab, you're taking a meter and you're connecting across those two terminals. Yeah, that's what it means. If you change the measurement terminals, then your REQ will change. So as we see in circuit A, we start at the farthest end and we start reducing as we move towards the measurement terminals. So if you want to measure REQ at the left end of the circuit, we start at the farthest end, which is R4, and we move towards, we reduce the circuit one step at a time, and we move towards the measurement terminals. This is for theoretical analysis. And I believe you have done this before, right? In physics, what, 2, 3? 3, okay. So if I want to find REQ, I start at the farthest end. I'm going to say R4. What is the relationship between R4 and the next resistor, R3? Connected with two terminals connected respectively, right? So R4 is in parallel with R3. That's my symbol for parallel, by the way. In parallel with R2. So as we move towards the front, I can see all three of them are in parallel. And then once all three of them are in parallel, I can electrically and mathematically reduce them down to one single resistance. I will call it R5. You can call it anything you want, doesn't really matter. I simply take the naming convention or the notations that are already given to me in the problem. You can call it R, X, Y, Z, A, B, C, Batman, Superman, Iron Man, doesn't really matter what you call it. R5 is the parallel combination of R4, R3, and R2. And REQ is still measured between those open terminals. Now what do we see? They are in series. It's not as evident when we look at the large circuit up front, right? You have more than 3 connections, or we have more than 2 connections at the top node, right? We have 4 resistors connected right there at the top node. But electrically and mathematically, we can reduce those 3 resistors on the right to one single resistor. That is mathematically, okay? Not physically, we're not combining anything. Mathematically and electrically speaking, we can note R2, R3, and R4 as one single resistor, R5, and R5 and R1 are in series, okay? So REQ is R1 plus R5. So now you tell me what is R5. R5 is the reciprocal of the sum of the reciprocals for the resistors. So 1/6 plus 1/3 plus 1/2. $11? Anyone? I heard murmurings of 1. That is indeed correct. 1 ohm. 1 in relation to 6, 3, and 2. Smaller. right? Smaller, that means my answer more likely than not should be correct. If I get 1.9, that still doesn't ring off any alarm bells. But if I get like 2 or 2.1 or 2.5, then you should immediately think that is not possible. So my REQ is 2 plus 1, 3 ohms. All right, questions? How about example B? Any questions on A? Okay, how about B? REQ for B, we start at the farthest end. I have R4 at the farthest end. Then as I move towards the front of the circuit or the left side of the circuit, the next resistor up is what? R3. What is the relationship between R4 and R3? We look at the nodes. Sorry? They are in parallel. Okay. If you look at the two terminals of R4, they're connected exactly to the two terminals of R3. And so they are in parallel. So R4 is in parallel with R3. And it always helps to draw out the circuit diagram. So from this end, I would say this is R5, which is equal to R4 in parallel with R3. Always, always, always draw out your measurement terminals and you mark it in the circuit diagram. REQ is, what is it now? This is R1. This is R2. That's R5. R5 is a combination of R3 and R4 in parallel. Now that combination is connected by only one node. If it's connected by one node with no more than two connections, they are in series. And I can say R2 is in series with R5, which would then be in parallel with R1. Does everybody see that? Let's take a 10-second pause. Let me know if you have any questions. Yes. Sure. So you're talking about this top terminal right here? It's still the same because I'm looking at R4 and I'm just following. So I start at the farthest end. At the farthest end, I have R4. Then I look at the two terminals of R4. I follow the connection for R4 and I see that it's connected to R3. At the top, it's already connected. It's quite evident. But at the bottom, I might just follow that node, the terminal connection, and I see it's connected to R3. So if it's connected to both terminals of R3, then they are in parallel. That's the only conclusion we can take. The only conclusion we can make. Does that make sense? Kind of. Like here? What do you mean choose as in? Whether it's series or parallel. Okay. Yeah. So as I said, we just start at the farthest end right now. If you try to simply look at the circuit and determine, that takes a while to get used to it. So at the beginning, if you're trying to do it slowly for circuits, we take it slowly. We look at the two terminals for R4. One terminal is here, the other terminal is here. We simply follow the pathway. And so here, it's going to R3. And here also, it's going to R3. So then we simply take a look at those two connections, and if they are making a connection over there, then they are in parallel. Sometimes it happens that it could be neither in parallel nor in series. And it happens. Yes. So start analyzing from the left. There are different techniques. So I'm going to show one more technique here. And I've never come across this technique in any book. Doesn't mean that it's not out there, but what I do, or I would teach students to do, is you draw out two horizontal lines marking your measurement terminals. Okay, so let's say call this 1, I call this 2. And the goal is to draw out all resistors vertically, going from terminal 1 to terminal 2, because those are my terminals of measurement. So this is 1, and this is 2. What do we have first? When I start from 1, I have R1, right? So I will draw R1, and the other end of R1 goes directly to 2, so I'm going to drop that down to 2. Then what else is connected at node number 1? R2. So I'm going to space it out, and I draw it a little distance away, R2. And the other end of R2 is connected to R3 and to R4. So I'm going to split. I'm going to draw R3 and R4. The other end of R4, again, remember the objective or the goal is to start at terminal 1 and get to terminal 2. So if I follow the same pathway, R4 is connected to 2, and R3 is also connected to 2. And so I'd simply extend these lines and drop it right there. And that's it. I've accounted for all 4 of my resistors. And now it is quite clear to me that R3 and R4 are in parallel, which would then be in series with R2. This entire branch is then in parallel with this branch of the circuit. So then, yes, we would start from the left in this technique. But this technique almost always works for all kinds of circuits. Okay. The goal is, again, to start between our measurement terminals, start from the top and go to the bottom. And this will work. There are a couple of homework problems which have diamond-shaped circuits. And so this technique will work for those circuits. Okay, so I'm going to assign these as practice, kind of rather straightforward. And then let's apply this technique to a circuit with a source. This is the first analysis technique. I believe we are still covering prereq material, right? This is something you have done in your prereq physics classes. Maybe, maybe not. Anyway, so now the purpose of reduction is that we can apply that reduction technique to a circuit with sources, whether a source, voltage source, or a current source. Okay, this technique would work for all of them. The first thing you do is we remove the source from the circuit, and we calculate or we measure Req as seen by the source. So as seen by the source. And so Req as seen by the source would give me, what is Req here? We start at the farthest end. I have R3. R3 is in parallel with R2, which is then in series with R1. You don't need a calculator to do this. two resistors in parallel. What did I just say, right? Two resistors in parallel, product of the two divided by the sum of the two. What do we have? 1800 divided by 90. How much? 20 plus 10. My total REQ as seen by that voltage source is 30 ohms. Now I plug the voltage source back in. So 90 volts, and this is noted as VS. This is REQ, which is 30 ohms. And for the voltage source, which direction is the current going? Some hesitancy showing. It's going up. Yes, you are correct. So for a source, current always goes from minus to plus. And so if I was to give a logical direction for the current, I will call it IS, right? Again, assumptions, but assumptions are based on rules and based on logic. So IS is going up. Where else can it go except through R1? There is no other place for it to go. So it goes through R1. For passive components like resistors, inductors, and capacitors, current always goes from high to low, plus to minus. Conversely, it means when current enters a resistor, the point of entry is plus or minus. So voltage drop across R1 is plus minus this way. When the current goes through IS, through R1, hits the junction, it splits. Logical pathway is going down. Point of entry is again plus. Point of exit is minus. And because R2 and R3 are in parallel, the voltage across the two must be the same. So the same signs, plus and minus, apply to R2 and they apply to R3. That's how we make assumptions when we set up the problem. Sorry, that's how we assume voltage polarities and current directions when we first set up the problem. Does that make sense now from chapter 1? When we say we assign values randomly, but those assumptions are based on certain rules and logic. And that's how we do so. All right, 2 minutes left. Let's see. So current IS is VS over REQ from Ohm's law. And so it's 90 divided by 30 gives me 3 amps. Let me draw another. So now that we reduced it down to one single resistance, we found the current. We expanded back up again in the same exact reverse order. And so when I expand it up again, I would have a voltage source and I would have R1, and let's call this R4. R4 is the parallel combination of R2 and R3, which was 20 ohms. All three of them are in series, so the same current IS flows through all components. And I can write from Ohm's law again, VR1 is, actually let me write it on the side. VR1 is IS times R1. You're almost out of time. 3 times 10, 30 volts. And VR4 is IS times R4, which gives me 3 times 20, 60 volts. Apply KVL, 90 minus 30 minus 60 equals 0. My answer is correct. And once I have VR4, I can also calculate I2. I didn't write I2, but let's call this I2. and let's call this I3. So I2 would be VR4 divided by R2, which is 60 divided by 20. Oh, 60 divided by 30, 2 amps, and I3 VR4 by R3, 60 divided by 60 equal to 1 amp. KCL, 2 plus 1 gives me 3 amps. So my answer is verified. So you have a homework due tonight based on the series parallel connections for resistors. Let me know if you have any questions about those problems. And then I think the next homework after that is due on Wednesday, which is based on this technique. We will look at one more exercise, maybe even two next class. But get started on those homework problems also. If you get stuck anywhere, let me know. Okay, reach out to me. I'll have student hours this afternoon, also available via email and Zoom. Reach out to me if you get stuck anywhere. All right, we'll bid you a good day, and I'll see you all on Wednesday.